Hello everyone, my name is Matthew Halm. This is joint work with my advisor Michael Poza that we presented last year at the WAFER conference in Merida, Mexico. This work pertains to the physical modeling of robotics, specifically for manipulation. And we note that even for some of the simplest manipulation tasks, the tractability of analyzing the system's motion varies heavily as the system goes through different modes of operation. So for a simple grasping task illustrated here, at the beginning, there's no contact between the object and the manipulator, and smooth Lagrangian dynamics are a very effective way of analyzing and controlling this system. Once a firm grasp is acquired, a little bit of additional complexity is added in analyzing the frictional statics of the grasp, but the acquisition of the grasp itself is actually far more complicated to analyze because analyzing it effectively means that you need to capture the dynamics of frictional contact. And frictional contact is basically poorly behaved in every way that a model might be poorly behaved. There is a high degree of stiffness due to high feedback gains in the manipulator. There are discontinuities induced by impacts between the object and manipulator. There is a combinatorial explosion of hybrid modality when the geometry of the manipulator is complex, and even the most basic properties of models that we would like, existence and uniqueness of solutions are often absent. Our community has done a really good job of coming up with some conservative approximations for navigating grasp acquisition, but with conservatism comes an inherent limit on either the dexterity or the agility of the motions that you can accurately produce. So we asked the question of whether or not we can find a middle ground. Can we find a single model that is both vibrant enough to capture the essential behaviors of grasp acquisition, but also tractable enough to use for the entire manipulation task? To do so, we look towards Quasi-statics, which is a common paradigm of modeling used in manipulation. Here are a couple recent examples, one in multimodal, or rather multi-agent manipulation, and another in real-time model process control for planar pushing. The basic idea underlying all of these models is that we approximate Newton's second law with a force balance. Often, particularly for robotics, this comes with a changing of the input space to a desired velocity for the manipulator, which we assume the manipulator can perfectly track. This allows you to completely disconnect the internal dynamics of your manipulator from the manipulation motion. Under these assumptions, you can efficiently model the behavior using a linear complementarity problem, or LCP, that will be able to explicitly solve for the contact forces between the object and the manipulator and the resulting motion as well. The intuition as for why these are reasonable approximations is that as you take feedback gains to infinity and commanded accelerations to zero, Newton's second law approaches a force balance, and manipulators will assumably able to nearly perfectly track any desired velocity. However, by explicitly examining this assumption, we have discovered that this intuition doesn't hold up even in the most essential behaviors of robotic manipulation. To illustrate the problem, we are going to make rigorous this notion of convergence as feedback gains increase by modeling the way that the manipulator tracks a desired velocity as linear velocity feedback. The policy that is associated with this is parameterized by some feedback gains that are packed in a positive definite matrix K. And the feedback policy produces an input torque that, under the assumption of quasi-statics, is exactly equal and opposite to the force that the manipulator experiences due to contact with the object. Under these assumptions, we can explicitly solve for the actual velocity of the manipulator in terms of its command and this disturbance contact force. If you look at this formulation, you see that the difference between the command and the actual velocity is inversely proportional to the feedback gains. So we would expect that as K inverse goes to zero, that we would have that our velocity approaches the desired velocity. So here's one of the most simple possible examples of a system undergoing this policy. Here we have a rectangular gray object resting on a blue surface being pushed to the right by a rectangular blue manipulator. As the object slides to the right, there will be a frictional force between the table and the object that resists its motion. And under the force balancing assumption, we must have a feedback torque tau, and a contact force in between the object and manipulator, such that the net force on each of the manipulator and the object is 0. If you equip the system with a relatively small feedback gain near unity, you'll find that the object doesn't move very fast, but as you increase the feedback gains, the actual velocity of the manipulator, here shown in green, approaches to its command. However, if we make this scenario even just a little more complicated, say we wanted to grasp the object by squeezing inward on both sides with a manipulator with 2 fingers, we'll find that there is no possible way for the object to converge to its command, because under the rigid body assumption, there is no way that the 2 fingers will be able to move closer to each other. We can go through the same process as before and explicitly solve for all of the contact forces. And as before, under a low feedback gain, as we expect, the object isn't going to move very fast. And as the feedback gain increases, the object will be squeezed tighter and tighter. The contact forces will diverge to infinity. However, the net force remains small because the contact forces nearly balance with each other. And the actual velocity of the object and manipulator converges to something other than the command. And we believe that this velocity, shown in green, is an accurate prediction of how real systems will behave. Therefore, the main contribution of this work is to produce a model that is able to predict these velocities. So to confine the space of systems that we would like to describe, we limit ourselves to the manipulation of a single object that rests on a horizontal frictional surface. And we're able to formulate our finite feedback behavior model as a linear complementarity problem that is no larger in dimension and therefore no less tractable than the state-of-the-art model for non-grasping commands. Additionally, we were able to prove a number of very important qualities of this model, the most important of which is no matter what grasping or jamming behavior is commanded, our model will always predict a solution. Furthermore, if you do not command a grasping or jamming motion, the solutions of our model will converge to the solutions of the state-of-the-art pushing model. And as we saw in the simple example, despite the fact that individual contact forces might diverge to infinity, the net forces and therefore the velocities of the object and the manipulator will remain bounded even if you have extremely high feedback gains. Furthermore, the discrepancy between the commanded and actual velocity of the manipulator, as in the simple case as well, is emergent from the balancing forces that are inherently present in grasping. The big takeaway from all of these qualities together is that if we would like to predict the behavior that the system will experience with infinite feedback, then we can approximate that very well by using finite feedback as long as it's sufficiently high. To that end, we created a simulation scheme from our model that is a time-stepping scheme. It uses a semi-implicit Euler method, which replaces forces with net impulses over a time step. And again, we were able to prove existence of solutions over a single time step. To illustrate the capabilities of this model for synthesizing interesting motion, we give as an example a tabletop peg and hole manipulation task. So here you can see a blue object being manipulated by 2 red triangulator manipulators. And you can see grasping motion, jamming motion against the corner of the slot, twisting into its final orientation for final insertion. It's not only important that our model be able to create these interesting behaviors, but it's also important that these behaviors are physically reasonable. And to the end of verifying that, we have compared our model to a full dynamic simulation done in Drake. And here we have a simple example of a 4-fingered manipulator manipulating a square object in which it is squeezed and turned quite fast. And we see very good alignment between our model and the full dynamics. So in summary, we present a new quasi-static model that is able to handle grasping at no additional computational cost from the state of the art. We prove that it is very well behaved, both mathematically and with numerical experiments that are available open source on GitHub. And for future work, we have a 3D multi-body model as an extension to this one And we have some experimental validation for both the 2D and the 3D models forthcoming. There are also, some drawbacks to our model that we would like to highlight. The first of which is that we claim you can approximate infinite feedback with sufficiently high finite feedback, yet due to the lack of understanding of perturbation analysis for linear complementarity problems, it's not quite clear how high is sufficiently high. Furthermore, like all time-stepping schemes for a rigid body contact, we're only able to make a linear approximation of the non-penetration constraint. This can be rectified by solving a sequence of LCPs for a single time step, but that will, of course, degrade computational efficiency. Also, like the space of models that make an approximation of the surface contact friction between the object and the surface that it rests upon, the forces that result from these LCPs might be scaled by some unknown factor due to only being able to solve for a lumped term. This problem actually is not present in our 3D formulation, but it comes at the expense of a weakening of our conditions under which we can assert existence of solutions. So as a canonical example here, for a block resting on a ramp, for shallow ramps, a reasonable quasi-static solution is that the block is static, but for very steep ramps, there is no sensible quasi-static depiction of the behavior here. So thank you for your time, and that's it. Yeah.